Good morning, everybody. Thank you for the introduction. My name is Zvonimir Bandic. I manage Next-Gen Platform Technologies Department, Invest in Digital Research. We are focused, we have been focused on persistent memories for a long time, focused on controllers for persistent memories, both for memory devices and block devices. For networking, largely motivated by the networking access to the persistent memories. Also very invested and interested in emerging CPU technologies, again related, to persistent memories. The presentation today will be about exabyte-scale persistent memory-centric architectures, kind of trying to understand, once you're trying to, access persistent memory over the network, how exactly are you going to scale that, and how exactly are you going to leapfrog, into the architectures that we are going to need in, say, 10 years, when due to the growth of data, exabyte doesn't really become as confusingly large as it may appear today. And I owe a lot of thanks to Stephen Bates, who has generously invited me to present here. So thank you very much, Stephen. And another plug-in for you. So, all right, very good. I'm just going to run through the forward-looking statements. You've seen this before. So here is the agenda. I'm going to do a quick kind of a high-level marketing overview of the rapid growth in the data ecosystem, what's new, what's happening. Most of you guys already know this. It's a little bit of messaging. Then I'll start focusing, on some technical detail. And luckily, I'm also bringing some charts, some data, to show some good arguments where this is all going. I'll look first into where should we attach persistent memories. What are the different attachment points inside the computer where you can put the persistent memory? Then I'm going to look at some existing technologies, particularly RDMA, how we can access persistent memories today, how many nanoseconds and microseconds is that, how can that work? And I will also look into the compute state of the art, some of the trends that are happening, especially with compute accelerators. And then we're going to look into the persistent memory scale-out. Really, if you want to reach very large scale, if you want to reach tens of petabytes, hundreds of petabytes, if you want to get to the exabyte, really, what are we talking about? How many nodes is that? And what are the requirements that this puts on switches? What are the requirements that this puts on a persistent memory itself? We're going to look at some hard numbers to see really, to actually illustrate the true challenges, if you want to build this hardware. And I'll try to actually give some orders of magnitude for the latencies that are required, and then we'll go into conclusions. Diverse and connected data types. So as we have all witnessed, in the last 10, 15 years, there's this explosive growth of data, and all data is proven to be important. And anybody who records the data or who generates some data decides to keep it because it's so valuable. It's valuable today, and people are recognizing they may become even more valuable in 10 years. So no video feed ever actually gets deleted. It doesn't even get compressed. It's so valuable, you don't even know what you can get from it in the future. When we talk about data, we like to talk about big data and about fast data. What does it really mean? It means actually relatively simple things. As Jim has mentioned, right? Storage sales kind of exploded in the last 10 years, and this is actually going to continue. There is so much data that people want to keep and preserve, and this is what big data is. And it actually generates money because you can do a lot of processing on this data. In the last few years, deep learning-based processing became especially powerful and especially important because its ability to actually analyze images and movies. And analysis of that data really allows insight into data, making predictions based on the data, training your, an example, training your deep learning model to recognize features in the data, for example, to recognize faces in the moving images. And then on top of that sits something we call fast data. So what does fast data really mean? It can kind of mean two slightly different things. First, fast data means a methodology. It indicates that a processing on data is actually done closer to the actual point where data is collected. An example of that would be would be a video camera that is capturing an image in real time. And instead of sending this image back to the server, where you would want to store it and maybe do some processing, it's actually doing some processing at the very edge. So you can look at that image, perhaps use just the inference model based on a deep network that's been trained on a big data, and you're looking at the faces, tagging the faces, and just sending a metadata from the very edge device. Similar examples can be constructed with the smart storage devices. In SNIA and SSSI, we have been working on object-based interfaces for storage. When you create an object-based interface for storage that's a little bit smarter than your normal block interface, you're actually allowing interesting things that you can do now with those objects that are stored in the object storage device. And you can do additional processing on these objects and use the object interface just to communicate the metadata information inferred from the object. For example, you can do a search. So those are the, and if I look at the fast data from the hardware perspective, I usually see something that's sitting in a memory, something that's sitting close to the CPU, or something that has a processing ability very close to the to where that data is stored, which necessarily points to the memory, obviously. Now, from general purpose to purpose-built, another important trend, that's emerging in the industry, especially when it comes to the fast data, is this desire to process data where data is being generated. And if we look at the emergence of the fast data, the trend that is happening is trend of accelerators, and a need of these accelerators to be very close to where the data is being generated. And this is already creating kind of significant impact on computer architectures, where a lot of compute doesn't really happen necessarily in the CPU, but it's happening in specialized devices that need to be very closely coupled to the CPU at the fastest possible bus, at the lowest possible latencies, and then participating in a processing of the data. An example being a GPU card, or a specialized ASIC that people are using for deep learning training or for Bitcoin mining, etc. And finally, workload diversity. So these the explosive growth of data, the data analysis, has actually led to some new workloads. And if you are looking it from perspective of the hardware, for the new workloads that are happening on the fast data, they're very memory-centric, very logically, because you need to have some processing capability close to the data. So from the hardware perspective, these are happening in the memories. And from the accelerator perspective, you're using GPU devices, purpose-built ASIC to actually do some processing on that data. And then if you look at the big data is really still very block I/O device-centric, very storage-centric. So this is what's going on at high capacities, HDDs and SSDs, and it's typically access with the storage semantics. So we kind of mentally associate big data with large disks and a storage semantic or block I/O semantic, and we mentally associate fast data with memory devices, which are like a DRAM or SRAM caches in the processor, and with purpose-built accelerators that are actually analyzing that data and that have processing cores and caches of their own. All right, so let's get down to some interesting details. I believe, I can see some people are taking images. I think SNIA will provide PDF of the presentation on the website. At least I made sure we got approval for that. So. But you are and okay. And if you email me, I'll send you a PDF too. No problem. So where should we attach persistent memory? So what are the obvious choices that we can do today? Well, we can attach it to the CPU bus, like the bus that we have today, putting dual inline memory modules and DDR cards, like a Viking Smart is showing there in the demo room. And in that case, what is the logical interface? So logical interface in case of DRAM is going to be DDR3 or DDR4, And in the case of persistent memories, there is some proprietary interfaces, and there is also JEDEC industry standard called NVDMP, which is really focused specifically on a persistent memory. When you look at that CPU bus, what are the quickly pros and cons? Pros that I like are low latency, or lowest latency that we know of today, how we can attach something to the CPU, high bandwidth, power proportionality, and coherence, although coherence is really implemented to the memory controller, but yeah, you don't have to worry about it. In terms of the cons, memory controller has to implement specific logical interface. So there's this very tight coupling that exists with the CPU. So you either have to design persistent memory with a specific CPU in mind, or you have to build industry standards that can allow plug-and-play functionality. It's not very well suited for stochastic latency behavior. That's one of the troubles of the DDR bus. It's really evolved together with the DRAM, which has a very precise non-stochastic latency behavior. In terms of persistent memories, this is a little bit different, and that's why NVDMP standard was actually required to bring some asynchronicity into the protocol. It's not hot pluggable. No computer system is going to like somebody reaching in and removing the memory. That's fatal. But this is something that we like for storage. And if you actually have a PCI Express SSD in a server, you can actually hot plug it in, and you're not going to crash the server. And finally, BIOS gets impacted. So what are the other buses? We can have a CPU serial bus, and this is something that's actually very, very interesting. It does exist out there in the open field. There is a DMI on IBM Power 8 servers. There is several standards that people are very seriously working on, OpenCAPI, CCIX, Gen Z, and RapidIO being some of the examples. And you can get high bandwidth, you can get significant pin reduction on a CPU, you can get a higher memory bandwidth to CPU, and again, you can expose coherency to the memory controller or a CPU, but in some cases, some of these standards, like CCIX and CAPI, which is a predecessor to OpenCAPI, actually try to put the coherence into the protocol itself, which is actually very interesting for scale-out. And finally, as a present-day option, similar to the DDR, and maybe as the most universal one, there is a PCI Express. There is a standard, at least for a block device, called NVMe. It's a standardized, it's platform independent. Latency is low enough for storage, questionable for memories, and I'll show some data. And it's very easy for RDMA integration, which is important when you need to do the scale-out. You will actually inherit delays due to the network, and at that point, PCI Express is not that bad. And finally, it's hot pluggable. Okay. So the emergence of memory fabric. Memory fabric, what does it mean? It means different things to different people, and you kind of have to start building things in hardware so you can tell people this is what memory fabric means to me. So I don't think I have exhaustive list here, but at least these are things that come to my mind when I think about memory fabrics. So the first thing is, if I have an architecture shown like here, if I have a page fault trap is actually going to lead to the RDMA request with my RDMA-capable network interface card, say InfiniBand or Rocky. I'm going to incur a context switch and some software overhead that's relatively expensive. But from that point on, my NIC card is going to actually take the full responsibility for me and deliver me a piece of data into my memory. And it's going to do this in a fairly automated way with the minimum involvement of the CPU, which is actually very good. And I'll show some latency data on this. The second thing and second and third things is something that doesn't really exist commercially yet, but we're trying to build it in the lab, and I'll show you some of these things. The second thing is to actually do global address translation management in software, leading to the load store accesses across global memory fabric. So it's a mouthful, but really what it means is if I cannot get a block from my caches, if I cannot get block in my local memory, I'm actually going to go over the dedicated network. And one example here that people are working on is Gen Z. I'll show you some data later. I'll actually go to a dedicated memory fabric network, and I'll get that 64 bytes of data. I'll get that cache line from some other node in the system and get it back. And so that's the second way. And finally, the third way is something that we have been working for a long time, and that really requires kind of close coupling to the processor itself, is to do the coherence protocol scale out. So every processor that that carries multiple cores has its own coherence protocol. And the interesting thing is you can put two processors in a dual node or quad node system, but you don't have to stop there. You can actually scale this out on a much larger scale. You can go on a cluster size scale with the coherence protocol. And in that case, you're really going to need global page management. But the nice thing about it is you do not you will minimize your software overhead. So with this kind of architecture, you're really getting potentially the fastest possible access to that memory, and even more importantly, you can have a coherent memory, so all these processing elements can share the same memory, which is very convenient for accelerators. Now RDMA networking. So this is the most mature technology. You can buy adapters from multiple different companies. And I'm showing data here. I'm not going to go through every single step, but we actually look into the 16-byte RDMA read request. And I like to show the 16-byte example because sometimes people think about RDMA networking only in the context of getting 4 kilobytes across the network. But actually, with InfiniBand, you can go as low, much lower than that. You can actually pull a cache line, or you can pull 16 bytes. So yes, it can be used for the memory applications. And if you actually look at all the steps, what's really happening when you do that RDMA request, the total latency is about 1.6 to 1.8 microseconds. And the interesting thing about it, most of that time is actually spent in the protocol. Most of this time is spent into different things that you have to do both on your local and remote HCA. And every time you kind of touch PCI Express, you are potentially risking to spend hundreds of nanoseconds. And I'm glad to see Chingbo. I have to plug Chingbo in here. There's a Chingbo Wang there in the first row. Chingbo is the first guy in my group many years ago who started plotting diagrams like this, kind of showing the latencies first on a PCI Express and then later on InfiniBand. So the interesting thing about it, obviously hardware today is built to be modular, so you can put things together. But there are nice opportunities here by integration. If you actually start integrating a NIC into the processor that's initiating a request, or a processor and target, or preferably both, kind of making it symmetric, there's actually a very nice opportunity to actually cut this latency and get it into a sub microsecond range. So that's an interesting thing that we're looking into. And here is the data. This is the data from, I think, 2015. Martin Lukerboden, Chingbo, and Dan put up this system together with Mellanox. We had a client, and we had a remote device that was implementing a key value store. And we actually look into what kind of practical latency we can get by submitting multiple key requests and just measuring the statistics. And here is on the target side, we implemented the PCI Express memory map device, and we used the commercial phase change memory component from Micron. And I'm showing two pieces of data here. In the dark is the DRAM data. So this is the data. If you implement your key value store with the DRAM on the key value store server side, you're actually going to get about 1.6, 1.7 microsecond latency accessing that data. If you use a PCI Express memory mapped card with PCM, it's going to be a little bit slower, but it's not that much slower. That's an interesting and nice thing about the PCI Express and scale out. Once you incur network latencies, PCI Express becomes kind of nice and still relevant today. So yeah, the latency there is about, I would say, 2.2 microseconds. And this was kind of the first experimental system that we have built where we kind of, allowed persistent memory to scale out beyond the scope of one node by actually building two-node system. So compute accelerators is something that's actually emerging today, becoming very relevant in the context of machine learning, both machine learning training and machine learning inference. And it's driving a need for scaling of the memory fabric. People like to build a custom hardware, custom ASICs. They like to use general purpose GPU cards. Some really like using FPGAs because of their flexibility. In all of these cases, you need to do a processing on data. And in all of these cases, if you want to access that data, you need to access memory. And in some cases, you want to access the shared memory. And this is where memory fabrics are becoming very, very relevant. And this is all leading to something that people call data-centric architecture or memory-centric architecture. Pretty much means the same thing. And what it means, you have all this data that's being generated, and this is the data that you can actually derive revenue from, but you need to do processing on this data. And you want to make this processing as efficient as possible. If, for example, you don't want to keep shuffling data back and from your cameras to the server, you want to do maybe some local processing. And in all cases, you want to have access to all the memory in the system, which is why I want to have a shared memory. So this kind of future vision involves the pool of data that's bringing the revenue, and then multitude of CPU devices, GPU devices, FPGA devices, custom ASICs, everything that's actually used to massage and process the data. So we talked about this already. Probably the something that occupies a lot of my time these days is thinking of what are the latency requirements for the memory fabrics across the board. What's the requirement on the memory itself? What's the requirement on the interfaces? What's the requirement on the network? And what's the requirement on network switches? So I'm going to try today to kind of get down and dirty, to some numbers. It's non-trivial to determine the threshold latency for which CPU load operation still makes sense. We kind of all know intuitively if CPU load is going to take 10 microseconds, you're going to stall that core for a really long time. It doesn't make sense. Better that to make it a I/O device. But if it's 10 nanoseconds, it's fabulous. It's like your LLC. But what about if it's 500 nanoseconds or 400 or 800? So that's an interesting range. So what we've done, we took a standard Intel Xeon computer. We played with BIOS to slow down the DRAM to kind of generate DRAMs of different latencies straight into the BIOS, and we ran a bunch of benchmarks. And by doing that, we kind of persuaded ourselves that if you have latency that's around 500 nanoseconds, you can still call this device a memory, and it still makes sense to go ahead with the memory semantics. This boundary is not hard. It's not like exactly 500 and 502 doesn't mean death. But it's kind of a good engineering estimate, and it can be very workload dependent. Somebody may find an important use case where perhaps 1.2 microsecond for memory would still be okay, and somebody will find a use case where 1.2 microsecond would make more sense as a block device. So this is possible. So this is one piece of data. The second piece of data is, okay, scale out. When I say scale out, what do I mean? I mean like take nodes, and I'm putting a lot of computer nodes together in a cluster. And I really want to look at the exabyte scale because that's where a lot of our collaborators in academia are getting really excited about. But it's scary, so I'm going to start with petabyte and tens of petabytes first, as a kind of first ticks on that scale. And I have to assume something about the memory itself. So by looking at the commercial components from Intel Micron that came out, and by looking at different things that are happening in research, I'm saying, okay, let's assume 256 gigabits per die. And if I assume that, that means that with some reasonable power assumptions, I can get to 8 or 16 terabytes of memory per one node. And now, if I look at the petabyte or 64 petabytes, now I can estimate how many nodes I need. And this is where things get scary. This is where things get really, really scary. For petabyte, 64 nodes, okay, it's not that scary. We still kind of know how to pack that into a few racks. But obviously, when you go tens of petabytes, you're now start talking about thousands of nodes. And that's a lot. That's a lot because no matter how smart of information theorist you get, no matter how smart of the topology of cluster that you build with this, even if you have a specialized workload, you are going to incur a lot of hops in that network if you're trying to access memory on another node. For petabyte, it would be 8 hops back and forth. For 64 petabytes, it would be 48 hops. And that's a lot of hops. There are some paths for improvement. You can increase dimensionality of the network topology. It's expensive. It's going to lead to more cables. You can improve power density envelope of the memory. That's my most favorite one because I'm not directly involved into design of memory, so I want to pass it to somebody else and tell them, well, if you give me 8 terabits per die, this is all going to get much, much better. But you know, and you can look at the improved topologies, specialized workloads that kind of gives some opportunities as well. What does this mean to a switch latency? Well, if I'm looking at 8 hops across the cluster, and if I want my system to still behave as a memory, meaning if I want that total latency to be in a 500 nanosecond to 1 microsecond range, very simple arithmetic gets me into a switch latency of 50 to 100 nanoseconds. This is super tough. This is something that's going to scare the networking guy, and you are not showing him the 64 petabyte stuff because you're dividing by 48, and this looks really, really scary. And so I just added this bullet here. Larger cluster will lead to significantly tighter latency requirements. But yeah, pretty much would get into 10 nanosecond range. How do you handle these things? Well, you need to start looking into memory fabric protocols itself. And the approach that they have taken there, we are looking at what's available today, what kind of systems I can build today in the lab and start doing some interesting measurements. So obviously 25 gigabit per second IP is available today. And new protocols are needed. You know, Ethernet has really been developed specifically for storage, for reliability, for serviceability. If you're talking about the memory, there's a lot of opportunities. There's a lot of things that you can strip out from the protocols. And what we have been playing with, we have been playing with some FPGAs and also from some custom ASICs. I'll show you on the next page. And we have been using a P4, which is a hardware definition language for networking switches, to kind of play with different protocols and see what kind of optimizations, actually what kind of things we can strip from Ethernet to make things faster and to get latency lower and lower. And this is kind of a thing that's relatively easy to do. Once you start using P4, we used initially FPGA. Now there is a commercial ASIC called Tofino from company Barefoot Networks. And for example, we implemented Gen Z. We were members of the Gen Z. We looked at the protocol. It didn't really take that long. It took like a few weeks to kind of implement the Gen Z switch. And this is now really cool. Now actually you have a platform that does something that's actually a memory fabric. We're building some Gen Z devices, and we're really trying to get down and dirty with the nanoseconds and microseconds to understand where this is really going. And finally, just as a piece of the vision, we are building this platform that kind of looks like this. Basically uses Tofino as a centerpiece, uses the Gen Z developed standards for the connectors, and it's allowing us to put a memory cards, persistent memory cards, general purpose processors, and dedicated accelerators all at the common fabric, and to kind of start evaluating, okay, this is how I'm thinking to scaling memory, and this is how I'm envisioning peripheral compute devices and machine accelerators to be accessing the shared memories, and these are the benefits that I can get from that memory fabric. And so to conclude, I think there's just about 1 minute left. The RDMA networking is really relevant for the memory fabric. It's a hardware we can get today. It's fun to play with. The typical measured latency for single back and forth is in 1.6 to 1.8 microsecond range. not really a memory, but can definitely be used with the memory semantics. From performance perspective, achieving 500 nanoseconds fabric latency across exabyte scale, and I really started with petabytes and tens of petabytes in my numerical analysis, this puts significant pressure on the persistent memory power and density. It puts a lot of pressure on the components. We really needed components to improve even more from amazing point where they're today, and puts significant pressure on a memory fabric switch latency and underlying protocols. And protocol innovations are obviously required to fulfill latency, throughput, and RAS requirements. So, thank you very much. I don't know what's the format. Do we have Q&A?
Thank you. We could probably take one question.
Okay.
Any questions? No? Thank you,
Cool.
Zvonimir.
Thank you. Thank you very much.